Hello everyone! In this lesson, we will learn the second chapter, tunnel ventilation resistance. In this chapter, we will learn how the resistance of airflow in the tunnel is generated, how to evaluate the ventilation condition of the tunnel ventilation system, and how to improve the ventilation conditions of the tunnel ventilation system. In the first section, we will learn the wind speed distribution on the tunnel section. When the flow velocity is low, the fluid particles do not mix with each other and move in layers along the direction parallel to the pipe axis, which is called laminar flow. When the flow velocity is large, the moving velocity of the fluid particles changes at any time in size and direction, becoming a mixed turbulence flow, which is called turbulence. Reynolds number is used to judge laminar flow or turbulent flow. The formula is as follows, where V is average flow rate, D is pipe diameter, is kinematic viscosity coefficient of fluid. In the actual engineering calculation, Re equal 2300 is usually used as the criterion for determining the flow pattern of the pipeline for the sake of simplicity. When Reynolds number is less than 2300, it is laminar flow. The experimental methods for testing laminar turbulence is as follows. Step 1. Slightly open the outlet valve to make the water flow in the test pipe. Have a stable and small flow rate. Step 2. Slightly open the small valve of the small red liquid tank to make the colored liquid flow out from the steam pipe. At this time, it may be seen that the colored liquid flow in the pipe and the water flow in the pipe flow forward along the axis, synchronous in the straight pipe, and the colored liquid presents a thin straight line, which indicates that under this flow state, the particles of the fluid do not move transversely perpendicular to the main flow direction, and the red straight line does not mix with the surrounding liquid, but flows forward in a clear hierarchy, that is, in a laminar flow state. Step 3. When the outlet valve is slowly opened to a certain opening, it can be observed that the red straight line begins to pulsate, but the fluid particles have not reached the degree of mutual exchange. At this time, it is the critical state where the flow state starts to change, and the flow rate at this time is the critical flow rate. Step 4. Continue to open the water outlet valve. The transverse position of the fluid particle will occur, and the red line will gradually diffuse and mix with water, and the flow state at this time is turbulent. Step 5. After that, if the outlet valve is gradually turned down to a certain opening, it can be observed that the flow state of fluid changes from turbulent flow to laminar flow. Continue to close the valve. The thin straight red line will appear again in the Reynolds curve, and the fluid flow state will change to laminar flow. For the non-critical section of the tunnel, The pipe diameter in the Reynolds number shall be expressed by the equivalent diameter of the tunnel section. The equivalent diameter formula is as follows. Therefore, the Reynolds number of non-critical section tunnel can be expressed by the following formula for tunnel section of different shapes. The relationship between perimeter U and sectional LS can be expressed by the following formula, where C is section shape factor. Trapezoid C equal 4.16. Spherical arch C equal 3.85. Semicircular arch C equal 3.90. In the porous media such as golf and rock stratum, the flow pattern discrimination criterion of L is expressed by the following formula, where K is seepage coefficient of caving zone, L is roughness coefficient of filter belt. When the Reynolds number is less than 0.25, it is laminar flow. When the Reynolds number is greater than 0.25 and less than 2.5, it is transitional flow. When the Reynolds number is greater than 2.5, it is turbulent flow. The physical parameters such as viscosity and the pressure of each point in the wind flow fluctuate irregularly with time, which is called turbulence fluctuation. Time average speed. Instantaneously, speed Vx with time tau changes, although its value is constantly changing. In a sufficiently long time period t, the flow velocity Vx always fluctuates around a certain average value. Wind speed distribution in tunnel. There is still a linear moving sea level near the wall, which is called the linear boundary layer. Its thickness dirt becomes thinner with the increase of Reynolds number, and its extent has a great influence on the flow resistance, heat and mass transfer processes. Outside the linear boundary layer, from the wall to the tunnel axis direction, the wind speed gradually increased and presents a parabolic distribution. The ratio of the average wind speed V and maximum wind speed Vmax on the section is called the wind speed distribution coefficient, expressed in kV. The smaller the roadway wall, the greater the wind speed distribution coefficient. That is, the more uniform the wind speed distribution on the section. For masonry tunnel, the wind speed distribution coefficient is 0.8 to 0.86. The wind speed distribution coefficient of the tunnel supported by wooden shed is 0.68 to 0.82. For the unsupported tunnel, the wind speed distribution coefficient is 0.74 to 0.81.